Hello everyone and welcome back. Now we're almost at the finish line for the May-June 2023 series that we had begun for Physics AS level. And we were on paper 2, variant 2, right? And before we go ahead and approach question 7, I would highly encourage you to check out all of the questions 1 up to 6 that we have uploaded previously. You can either find them in our video list or we even have a separate playlist dedicated to that. So do check that out before we go ahead. So now with that out of the way, let's begin. Now here's question 7 part A. A battery of electromotive force or EMF 9 volts and negligible internal resistance is connected to a light dependent resistor or LDR and a fixed resistor as shown here. The LDR and fixed resistor have resistances of 1800 ohms and 1200 ohms respectively. First, we have to calculate the potential difference across the LDR. Now, if we go back here, we want to find it for specifically this resistor, the one with 1800 ohms, because from its symbol we can tell it's an LDR, right? And whether it's an LDR or a fixed resistor, the formula for potential difference that we would use is pretty universal. It would just be V equals IR, right? But in context of this circuit, this is not just any circuit, but rather a series circuit, right? Where the current that's flowing through the battery, which we would label as the total current of the entire circuit, that's the same current flowing through the LDR and the same current flowing through the fixed resistor. Which means that even if I want to find the potential difference V for the LDR, let me label it V LDR, the current could definitely be the total current flowing through the circuit, whereas the resistance would definitely be the resistance of the LDR itself, right? So let us first solve for the total current before we use this formula. Now the total current can be found out using basically a rearranged formula or a rearranged version of the above formula, which would be V over R. But this time, for total current, we would use total potential difference and total resistance. The total potential difference is nothing but the EMF of the entire series circuit, whereas the total resistance would just be an addition of both resistors of the LDR and the fixed resistor R. We can now plug in our numbers, so we will get 9 over 1800 plus 1200 gives us 9 over 3000, and solving this will give you 0.003 amperes. Now that you have the total current figured out, now I can use this above formula. So the potential difference across the LDR would just be 0.003 times the resistance of the LDR, which is 1800. Plugging this into your calculator, you should get in the end 5.4 volts. So that's your answer for part A, right? Now let's do part B. The circuit in A is now modified by adding a uniform resistance wire XY and a galvanometer as shown in figure 7.2. The length of the wire XY is 1.2 meters. The movable connection Z is positioned on the wire XY so that the galvanometer reading is 0. Part I says to calculate the length XZ along the resistance Y. Now here we must understand that when the galvanometer reading in this case is 0, that basically means no current is flowing. The only situation where there is no current flowing is when the potential difference across 2 points is 0. Now here when we say 2 points, we can focus more so on XZ rather than ZY, only because the question is referring to XZ so much. So we repeat, the potential difference across any 2 points, if it were any other circuit, we would say that the potential difference across 2 points is 0. Now in this scenario, when we say 2 points XZ, we see that there are two paths that can be considered. One is the path along the wire, which I'll highlight yellow over here. This would have ideally a potential difference Vxz. Let's call it Vxz. And then there is another path that's being shared across the points xz that we can highlight with a different color. Let's do it with red. It's basically this path, specifically the path including the LDR and not the fixed resistor. We already know what that potential difference is. For now, I'll just call it V subscript LDR. Now, when we say that the galvanometer reading is 0, we generally mean that there is no potential difference across 2 points. In this kind of a situation, we claim that when we claim that the potential difference is 0, what we mean to say is that the potential difference across the points xz in the wire, Vxz, is equal to the potential difference across the 2 points in the other path. In this case, that would be VLDR. So to solve this question, we need to highlight that the potential difference across xz is equal to the potential difference of the LDR. And we have already figured that out using part A, which was 5.4 volts, right? Now using this, we can now figure out the length, but then you might wonder, okay, how do we do that? This is where we have to remember that in this situation where now there's this additional wire being included, we have to somehow relate the potential difference V with the length. Now, we can think of this logically, where if we just think about length, specifically for the resistance wire, we know how the length tends to relate with the resistance a lot, right? We have in fact recall from physics lessons that the resistance across any conductor is directly proportional to its length, right? We also know that for the same amount of current flowing through a conductor, the resistance is also directly proportional to potential difference of that conductor, right? Again, knowing that we have the same amount of current flowing through. So in this kind of a scenario, we can relate these two proportionalities and claim that the potential difference across any conductor is directly proportional to the length of the conductor. This is what we'll be using to our advantage now, where we can basically we can construct a ratio of potential differences and equate it to the ratio of the lengths. So in this case, we can rearrange write a ratio as follows. Vxz, potential difference across the point xz, we can compare it in fact with the total potential difference across the entire wire, let's call that xy. That is equal to the length across xz, which is our unknown, divided by the total length xy. Now you might be wondering, why are we interested in the total length? Because not only are we given the total length of 1.2 meters, but we know that for this kind of a parallel circuit, we know that the 9 volts is distributed equally across xy above and xy below, right? So with this in mind, the potential difference across the points xy would just be equal to the EMF 9 volts. So now I can plug in the values. 5.4 divided by 9 equals the length xz that we wish to find divided by 1.2. So now it's just a matter of solving for the length xz, 5.4 times 1.2 divided by 9. Plugging everything in, you should get your answer to be 0.72 meters. Right? Now let's look at the next part. The environmental conditions change, causing a decrease in the resistance of the LDR. The temperature of the LDR remains constant. State whether there is a decrease, increase, or no change to the intensity of the light illuminating the LDR. So let's do that first. So an LDR is a light dependent resistor, right? And we know that for a light dependent resistor, the resistance of the LDR, I'll just call it resistance, is inversely proportional to the intensity of light shining on the LDR. Since we're told that there is a decrease in resistance, that can only be caused by an increase in the intensity of the light illuminating the LDR. So we'll mention that in this situation there is an increase. Now let's look at the next part, the total power produced by the battery. Now we recall the formula of the total power produced by the battery, that is the EMF of the battery times the total current supplied by the battery to the entire circuit, right? Now we remind ourselves that in this situation, nothing is really changing in the battery, right? So we don't really expect the EMF to change. So then the question is, does the total current change? Well, let's see. We're told that due to a change in the environmental condition, there is a decrease in the resistance of the LDR. Now, if there is a decrease in the resistance of the LDR, that means there would definitely be a decrease in the total resistance of the entire circuit, right? There has to be. Now, when there is a total decrease or a decrease in the total resistance of the entire circuit, that will mean overall there is less resistance offered by the entire circuit, meaning there will be a greater flow of current, right? Which means we expect the total current to actually increase. And when that happens, while keeping the EMF constant, the power ends up increasing. And so we'll write an increase over here. Now finally, the last part, the length xz so that the galvanometer reading reads 0. Now we've already established that the only situation where the galvanometer reading reads 0 is when Vxz equals VLDR. Now we've already mentioned that the resistance of the LDR is decreasing, which would definitely cause the potential difference across the LDR to decrease as well, which would automatically mean Vxz has to decrease as well. When Vxc has to decrease, since we already established that the potential difference is directly related to the length of the resistance wire, that means we will definitely have to decrease the distance between xz so that the galvanometer reading reads 0 once again. And so the last part will include a decrease. Alright, so this was a very thorough revision of everything that has to do with current electricity, and we hope this helped you. Okay? In our next video, we will finally wrap up with this entire paper 2 variant 2 by attempting question 8 together. So see you there. Thank you.